Oh, okay, let's go. Okay, I think I'm live. Awesome. Here we go. Had a bit of mic problem just a couple minutes ago, but I think that's resolved. All right, welcome to another live stream of bubblepins. So today we're going to cover, we're continuing on the previous topic. The last topic was about tornado motion and how to develop that tornado motion. And today we're going to take that and build up on it and take it to the next level and convert our tornado motion formula or vex code that we developed and convert it into a velocity volume or a vector field that we're going to feed into different types of simulations. And due to time constraints, I've prepared a Pyro simulation example, and we're going to work on a little bit on the Vellum paper example. Because last week in the paper, and at near the end of last week's live stream, I had shown you how to feed in our pop force tornado motion and feed it into a Vellum simulation where I had a bunch of scrap pieces of paper lying on the floor and it was being pushed around like this in a tornado motion. But this was driven by a pop force with the vex code that pushes using the cross product that I explained, demonstrated in the basic concepts last week, which is not using velocity volumes. So today we're going to take that into convert our pop force into a velocity volume. And a velocity volume is like a vector field. And this is more convenient, more reusable, and more flexible to use for different types of simulations. So we're not just restricted to using only particles. Because pop force is only useful or compatible with particles. So anything with particles should be good. For example, the Vellum simulation has particles. So we're able to manipulate some of the points using the pop force. And packed RBD has particles. It has to be a packed RBD though. Flip fluid is flip particles. Grains should work too. I haven't tried it though. That just sparked an idea last night. I was like, I haven't tried plugging the tornado motion into grains, which I think will look awesome. What else am I missing? There should be flip fluid, Vellum. Let me see my list. Vellum. Now the only thing it doesn't work, I know that it doesn't work right off the bat, is that you cannot use the pop force with Pyro. Because Pyro doesn't have points to be, it's a volume. So it has voxels. So this is where the velocity volume comes in handy. And we're going to explore the difference between using, I'm going to show you an example where I feed in pop force, the tornado motion, into a Vellum that we've seen last week. And then I'm going to show you what it looks like with a velocity volume fed into the Vellum paper tornado. Okay, first things first. Welcome a new member, Song. Welcome to the bubblepins world. I hope you enjoy the content. So, if you decide to join the bubblepins membership, you do get exclusive access to the HIP files and HIP projects and some of the exclusive Perk 2 gets some of the exclusive videos that I have made in a while back. So I haven't had time to do more exclusive video content for Perk 2, which is on my back burner list. But Perk 2 gets exclusive HIP, the digital content, gets everything. Perk 1 gets a selected amount of the HIP files. It doesn't get all the HDAs, it doesn't get all the projects. It gets a selected amount. So that gives me a way to sort of draw the line between Perk 1 and Perk 2. Okay, for today. Now, last week I went over all 4 basic concepts and built, and it was building up from the cross product all the way to a formula that we can code into Vex for tornado motion. So that was last week. Now we're going to take that and we're going to explore how to create volume velocity, how to feed it into different types of simulations like Vellum, and the difference between using pop force and pop advect by volume, which is this is what we were using last week, the pop force, which is the Vex code, the pop advect by volume, which is a velocity volume or vector field. And we're going to finally plug it into a Pyro simulation. And some of the examples you see on the screen right here are Pyros. This here, I really like how this turned out. This is the tornado. So you can recognize the tornado shape right here, right off the bat. So this is the velocity volume that I'm displaying. This is not the velocity volume powering the Pyro. So we can actually plug this velocity or vector field into a Pyro and have this move the Pyro. But it looked really awesome just with the velocity volume already. I really like these curvatures. And if I used a lower voxel size, which means a higher resolution for a volume, I think this would look even better. But due to time constraints, because Pyro does take a while to cook if you go too low. I believe this was done with 0.03 voxel. So this was already took a while already. This here you see is from the custom. I took the tornado shape that we had last week and modified it a lot. And you get this weird shape here. It sort of looks like a horse. It's the tornado shape going up. Let me see if I can display this side by side. It's still this same tornado shape spinning up. Except here, it's going zigzag up and down. So let me bring up my trusty drawing program. I believe it's like this. Something like this. It's going zigzag up and left and right as it goes higher. So that's powered by a sine wave. And if I don't know if I should play this simulation. Oops, not this one. If I play the simulation a little further, I want to show you that I did make a lot of changes. I just want to make sure it's cached. Simple tornado, this is the one. Okay, it is cached. Okay. Otherwise, Houdini will start crashing. So let me skip to the end. Okay, here it is. So you can see that once it gets up here, once it gets up there, past this line right here, that height, it starts to spread. It expands a lot faster. So it grows a lot faster right up here. And that's because I added a bit of condition into the Vex code. If the particle is above a certain height, remove that inward force. Now, if you remember correctly from last week's, near the end of the live stream, I had mentioned that I added an inward force on top of our tornado Vex formula. So I had another vector that was contributing to the whole thing, to the whole tornado motion, and it was pushing it inwards to the center of the tornado, keeping the whole shape inwards. Otherwise, we would get something that looks like this, that would be spread out, that would gradually spread out like this. In order to keep that tornado thin line for most of the time, I added an inward force to push it back in. But once it gets to a certain height, for example, once it gets to this blue line right here, it spreads. I removed the inward force, so it spreads a lot faster. and we get that expansion that you see over here. So that's one of the modifications I did. Okay. Now I originally wanted to go over the modified version of my tornado in more detail, but I think that's not, it won't be as interesting. So instead, we're gonna do a little bit of reordering, and I'm gonna go over the velocity volume first, and how to create it and how to feed it into different simulations. And then near the end of the video, if we have time, I can go over how I modified the simple tornado. That's this, and made it look like something like this, with giving it a zigzag shape going up and all that stuff. It's very mathy. It's very Vex code related. There isn't that much Vex code. Actually, let me show you. Oh, that did trigger a cook. Okay, let me go back to frame 1. Here's the pop force. This is the one. Let me open this up. Let me make this bigger. So in order to make this text box bigger, highlight this, click it, focus it. So you can tell that this is not highlighted. Once you click it, this is in focus. There's this orange highlight around it. And then press, while the mouse is hovering over it, on your keyboard, press Control+. Just like how you zoom in and out in a browser. It's the same shortcut. Let's see. Let's go back up. So I just want you to see it. So all this Vex code is plugged into this pop force, which allows us to get, I want to run the cache one, just because the cache one is more efficient. I don't know why it's cooking though. But it's almost done. I'm not sure why it's cooking. It shouldn't have to, because it is running from cache. So this has a bit more modification. This is what I modified to get this. And let me bring up our original simple tornado pop force. Okay, so this is already cooking. We might as well stay in here then. So you can tell this is the zigzag look. So this is this. Let me place this in the right real estate. So this is this. And this guy is, this is the exponential one. The one that I wanted to show you was the one we had last week. Here, from basic concept 1. This is it. Oops. Let's go back. Oh, that's already here. Okay. So this is the modified zigzag one. This one here was the original. This will look familiar. This was the original tornado, the basic one, that just drives it up like that. So it's very, very simple. The one that I've modified has a lot more stuff to it. So it does have an inward power that keeps it together. So that's this thin line you see here, twirling up. There's also a sine wave here. This line here is what drives this zigzag look. Zigzag look here. That's what this line here does. It's a little hard to tell with that color. Yeah, that's what that line does. The next thing is I want to show you here this line. Force direction, turn direction. here. Now this line here is when it detects the height of the particles. If the height of the particles pass this line, then it starts spreading up. So you can see that the tornado starts expanding a lot more. It's no longer keeping this zigzag line anymore. So that's what this over here says. At P1, that means the height, because we're taking the y of at P. At P is the x, y, z position of each particle. So if we're going to take the one element, so it's zero based, at P, maybe I should draw this out. So at P is position. Now it has an x, y, z. It has an x, y, z component. We know y is the height. So at P, I just want to change the y. So that's going to be 1. That's going to be the y. That's like the height. Okay, that's better. At P, 0 would be the x. And this would be the z. The last one would be the z. So that's the second position. The first, zero index. First, and then second. So that's how we change just the height, or how to get just the height. So this is what I have right here. If at P, at the 1, is greater than 2. So once it exceeds, the height exceeds the second unit in Houdini, we're going to take the direction, and I'm going to just give it back to assign it to the turn direction. Which here is the normalized cross product. So it's going back to what it was before. Now I know I have a lot of stuff here. I've normalized it, and I have this turning power. This is just fancy stuff for me to control the power that it turns, the spinning rate of the cross product. So we're going to get more deep into this mathy stuff in this Vex code here near the end. It's more of I find it the less interesting things that we have that I have planned today. Okay, just bringing back my notes. Okay. Oh, sorry, I didn't see this. Thanks so much for explaining this. I tried so often to change one aspect and never found out how. Oh, the at P? Yeah. I've been wanting to do a Vex, more of a programming tutorial. However, I have really long explanations, so can you imagine what it would become if I had a Vex tutorial? I have to find a way to explain it in a more straightforward way. So I'm still working on that, but it's in the works. I'm trying to get a way to explain complex things more simply. Today modified. So I went over that a bit. Very vector. Yeah, so that's not very interesting, the mathy stuff. So let's get straight into why use volume velocity in Houdini. Now that's a very good question. I'm going to ask myself. Hopefully someone here is thinking the same way. Why use volume velocity? Now, why would you ask that question though? Why is that even a question? Let's go into that paper simulation that I showed last week. Let's go back here. Now let's take a look at this simulation. Let me just play it first. It is a bit slow. It's cooking for the first time. I would watch it all. Thanks for the hard work. Thank you for watching. Nori. I hope I pronounced that name right. Let's see. This is blowing it up. Oh, I think I have the wrong one. Shoot. Yeah, this is the pop. I wanted to show you what we had last week, which is using the pop force. My bad. So So let's take a look while we're in here. Let me pop this up. So this looks familiar, hopefully, because we just saw it 2 seconds ago. This is the tornado force, the very basic tornado force we have going on here. Okay, I'll just keep this open over here. Let me go back out and play. Okay, there it goes. This makes a little more sense now. And I do realize that the paper is going the wrong way. The particles are going the other way because I think I have this cross product crisscrossed. I believe this at P minus center and this axis is the other way around. In the particle, it's the other way around. I cross product the axes first and then the at P. So these two parameters were the vice versa. And that changes the direction. So, small tip. Okay, so here we see it blowing all over the place. This is controlling it simply by a pop force. I wish I could make that ground go away. But anyways. So this is controlling it. We have, oh, and another thing. This is a Vellum solver. In order to get inside that force, the dot net force that we want to modify, because this is quite new. The Vellum solver being on the SOP level here. This is something new in Houdini. I think they introduced it in Houdini 18. I can't remember. We used to have these dot nets, and we had to like add a dot network, and inside the dot network we could lay down like Vellum solvers, whatever solvers in here. Now there's the new age of Houdini. They're putting a lot of solver capability right on the SOP level. And this is incredibly handy and it speeds up the workflow. But there are some quirks to it that some people have asked me on the comments, is that how do you get into this? You simply just double click it. Just drop down your solver, double click it. It'll bring you right into the force network where you can hook up your forces. And that's what I've done right here. So you'll be given 2 output nodes, and the one that we want to use is the output force. Remember to put this orange flag on here because it defaults to the output source over here. But if you want to use a force, like what we're doing right now, we're using a pop force and we're chaining it we're dropping the pop force node onto it. That you have to use this one, this output. Remember to put the orange flag over here, which is the output flag, which tells Houdini to Vellum solver to use this instead of the other one. So this is the pop force that we have, and it's simply this tornado motion that we've seen again and again. And all it's telling each piece of paper to move in a circle, because we're calculating the cross product of every single piece of paper, and it's telling it to move in a circular motion, and that results in a tornado. So this is incredibly useful for something like a city, an urban city with a lot of pollution, and you can have a lot of buildings, which was something I wanted to work on, but I ran out of time. I wanted to put this onto my windy poster scene from last week. Now, where's that windy poster? Oh, it might have been last week then. Wow. Where is that windy poster? I'm sorry. Oh, here it is. So this windy poster scene, it would have looked perfect if I had these papers flying in a tornado fashion in here. That's to come soon too. So this pop force provides a direct manipulation. You can manipulate the vellum particles directly, and it gives you a very direct channel to modify it. There's no implication, there's nothing. It's very simple. The only complexity is that it's all in VEX code. Well, it's not all in VEX code. We have it in VEX code in here. So you do have to... Now, the simple part in this is that if we go back up to our particles, no, that's basic concept 1. So this is a pop net. This is a very simple pop net. And I'm just going to play it. And this is just the particles moving in a circle. But if you look carefully, I have a pop source, I have a pop force, and I have a pop drag. So really, all I just took was these two. Now, minus the yellow one. So this is the pop source. So this is irrelevant to the vellum. I literally took this, Control C. Go back up. Now let's go to that tornado, vellum tornado. Here. I'm going to move this aside. And I'm going to Control V. Now, this is the one that I had in our pop net. I'm just going to hook it up. Let's see what happens. Oop. Okay, I think it doesn't... Now, nothing is happening here because I don't think I have enough power. Because these vellum, the vellum paper here, you see, it does have weight. So it is a little different from the pop net. You do have to adjust the power a lot. So let's give it 10. So we're into the pop force. And what was working for the pop net, for the particle simulation, was a force of 1 going upwards. Now I'm going to put this 10 times. And then I'm going to replay the simulation. Okay, now you're starting to see it move. So there is a bit of adjustment other than control. You know, we're copying the exact same node. So this was working for the pop net. So this is incredibly easy if you like this kind of workflow. However, we're here today to explore volume velocities. So let me take this out. Let me put this aside. So let's put all this aside. And with volume velocities, we get this, we have to use this pop effect by volumes. But before I get into this, I want to show you the volume velocity first. Now that's basic concept 1. So let's go to it all starts with the particle system. It always starts with the particle system. And we're going to actually create a volume velocity. So this is the custom made one that I did. This one. We're not going to use this one. We're going to use this one. So this is spinning, and this is actually using another formula to do it. So that, but I don't want to get into this formula, this exponential formula. There's many ways to create the same tornado motion. So what I will do is let's go back to that basic concept 1. Let's come here. And this is something we recognize, this pop force and pop drag. So I'm going to copy this. And I want to paste it in here. Now, why would I do that? Because I could just use the other particle system. They're both particle systems. It's just that I have everything hooked up to this one. Okay. I'm going to put this aside. This is the one we're going to be using. And I want to switch it to the second one, which is this one here. And let's play it. Okay. Whoops. Too close. There you go. So we're getting that tornado motion. Awesome. So this is a particle system. Torus is feeding in the particles, scattering particles around the torus and the particle system here. Dot import extracts all that particle system data and brings it into the SOP level. So that's that .net thing that I just mentioned. Pop, I don't believe they have a pop solver right on the SOP level yet. Like, so this PopNet is still based off of the old-fashioned .net. And whenever you have a .net, you need a .import in order to bring it up back into the SOP level. And that's what we have here. And whenever you get confused, what is the dot level? What is the stop level? We can always take a look at this breadcrumb up here. So this is the stop level. This is straight from the object level here, which is the geometry contacts, which is the highest level of contacts in Houdini already. And then go back in. The procedural I've labeled it procedural animation. So this is the geometry contacts, which is the SOP contacts, SOP level here, which deals with all the surface operators it stands for. Now, once I go into this dot network, you'll see that it's a pop net here, which is a particle network, which is a type of dot net, which is a dot net stands for, I believe it stands for dynamics operator, which deals with all simulations of all sorts of types, Vellum, RBD, Pyro, you name it. Okay. That's your 2-second explanation of .NET. Sorry, because that's not the focus of today's video. That's why I just want to skim over that just a bit. Dot import here. Now we're bringing in all the particles, so we're getting all that tornado motion data here. I do something fancy, and I remove some of the bottom parts, but it doesn't seem like it's leaking through, so I can just ignore this. This is for other ones. I reuse this setup for many different types of simulations that you will see in just a bit. Now, I have here the tornado motion. It's just the null. It's being, I'm chaining this to my velocity volume. Let me bring this over. So now I'm feeding in our particle system into a point replicate. So I'm getting a lot more of this guy. If I play this, it's the same particle network moving in a circle in a tornado fashion, but with more of it because I'm replicating the particles like crazy. Now let's not worry about that right now. Let's just deal with our mini particle system, mini tornado particle. We need to convert this particle system into a volume, into a velocity volume. Well, if you ever did any sort of pyro simulation, you know that if you have particles and you want to convert it into a pyro, or you're creating a pyro source for your pyro simulation, you can always use the pyro source node. What this node does, it converts, it takes all these particles and it creates specific attributes for each particle and adds all this data in here for the particles and preps it ready for the pyro system in order for these particles to become a volume. So that's what a pyro source does. So let's take a look what it was before the pyro source. You can see here, we still have all that data left off from the particle system, like age, air resist, these particles being dead, which ones are dead. There's a force, hit. A lot of this we don't need. Here, in order to illustrate this, let me clean this up. Remove attributes. Right. Let's feed it in here. I believe I do need to keep the velocity though. But let's take a look. Pyro source, velocity, density, temperature. Okay, there's nothing in here because I have to play the simulation. Here, clean it up. Pyro source here. Yeah, I think I do need to keep a few. As I mentioned here, this is getting messy. Let me bring this over. I just want proper labeling. Okay, let's focus on this. So this is our pop net. Here, as I mentioned here, the particle system gives us a lot of information. The age, the air resist, I don't know if that's important, but it has velocity and force. So that may come in handy for the pyro source to convert that into velocity, density, and temperature. Oh, we just got a new member. Awesome. Slow Unicorn. Awesome name. Uncheck, remove unused points. Oh, did I have that? Oh, thank you. That was a good one. I'm so sorry. I missed that completely. Remove attributes, remove degenerate points. Okay, sorry. That was my bad. Yeah, you're right. Thank you so much. Drasco, thank you so much. I didn't even see that. So we do, if I clean it, and then you feed it into the pyro source, you can see that it puts in all this stuff here. Density, P, scale, temperature, velocity, and all this stuff. It adds this good stuff in here that needs to be it needs to be there for the pyro in order to convert it into a volume. We need that good stuff. We need all those ingredients. If I take a look into the clean, so I deliberately cleaned out all the particles, and at the same time, it was accidentally deleting the particles at the same time because I've had this remove degenerate primitives and remove unused points. Thank you, Drasco, for pointing that out. Because all I wanted to do with this clean node was remove the attributes. So if we come up here to the pop net right here, this is directly from the particle system. It gives us all this other ingredients. These ingredients may or may not be used by the pyro source to convert it into to add all the density, to calculate the density, P scale, and temperature. So I deliberately put a clean here to show you what this pyro source node is doing. It just creates these three nodes, that these three attributes that we need. Then it's still not a volume yet. It's still not a volume. So Jacob is saying hello from Germany. Hello. And then volume rasterized attribute. So this pyro source is still particles. We're still running on 4,950 points. So it's still particles. We don't have a volume yet. In order to get this into a volume, we need a volume rasterized attribute. This will turn it into a volume. So instantly you see a volume. So you do need the pyro source here though, because this will prep all the ingredients ready in order to get this volume rasterized attribute. Now I actually don't want to clean this because I did have a P scale here. I am controlling the P scale manually. So yeah, this is what it looks like. So this pyro source, if it detects, you can control how the pyro source preps the ingredients, which then controls the results of the volume. So if I lower this, increase this, there you go. So that's controlling the volume right here. If I have a P scale of 0, our volume is non-existent almost. This can control the coverage or the influence of each particle when converting it into a volume. So let's just see what this looks like. Let me turn this back into light background. So you can see the volume increasing. So this will become our volume velocity. Now we can actually, if you want a better, this is actually what I showed you with this. Oh, it didn't come up. This is actually this. It's actually the same thing. Well, this one here might be a higher voxel quality, like 0.03 voxel. And this one here looks a lot better because I am using a volume visualizer to view it. Without that volume visualizer, it looks like this. It still looks a little bit better, just because it's a higher voxel count though. But let me paste in my volume visualizer onto our volume velocity. So this is the volume visualizer. Now, how do I get this? Just tab, volume visualization. This is a way to get really high quality looks of your volume right from the viewport. So this is more of a debugging tool to actually see what you're doing, to actually see what it's coming out. So this doesn't affect your renders. This doesn't affect the simulation. It only converts whatever your volume has, and it tells Houdini how to display it on the viewport. Literally, this is a visual thing. So I'm just gonna give it a black node. Now the one that I've pasted over here is the same node, except it's very, I've already configured it, but we can do it quickly here. I think we can. Well, I do have my notes here, so I can, let's do it live, because this can get tricky to play around with. Now, before I actually do start showing you how to use this volume visualization node, you need to know that there is actually another node in that was introduced in Houdini 19. It's called the Pyro Vellum, and it does a very similar thing. It creates a very high quality volume and displays it right into your viewport. So let's hook this up and view what the Pyro Vellum does. So this is what what we're getting right now, because this is a very low voxel count simulation. So another thing, if you want to get as high quality render right for your Pyro right out of the viewport, there are a few things you need to tweak. One, you can use the old volume visualization that I'm used to, or you can use the new Pyro Vellum. That works too. And another thing you need to note is that you have to turn your display port to a higher setting. So the viewport here is optimized currently for best performance. So if you wanted a higher display of your volume, come over here, press D to bring up the display settings. Come over here to the geometry tab. And over here, you'll see volumes. In the volume section, volume quality. Now, this is by default at, I think it was normal, or was it low? I can't remember what was the default. But I've turned it up high. So you can see an instant feedback in the viewport. So this is what it looks high. I mean, they all look pretty bad just because I have a very low voxel count right now. This is low. This is high. I think this is better illustrated with one of the cached ones I have, because this one is cached out, so it makes it a little easier to show you. Let's take a simple one. So I don't have to cook it, is what I'm saying. The other one is not cached because this one, yeah, this is the same example I'll show you. Now let's take this. Let's take this. And let's do that again. High, low. So this looks awesome either way, just because of the voxel count. Low, but you can see more detail with the high. You can see that this is more detailed. It's less fluffy, I guess. And this is straight off of the viewport. I mean, I haven't even put the volume visualizer on already. Let's see. Oops. Let's put it in here. Let's slap it in here. Oh, that looks nice. I can even go higher. Like if you cook the simulation at a lower voxel count. So this is something we can go over just quickly. Now, how would you configure, how would you tweak the voxel count? We have a particle system here, and then it feeds it into our nice little chain of nodes, which we're trying to convert it into a volume. So clean Pyro, here we go. This is in the Pyro source. There's a particle separation. So this contributes to sort of the quality of the resolution of the volume. The lower this value is, the lower the particle separation is, the higher the quality of the volume. Let's see. And here, the volume rasterite attribute also has a voxel size here. Usually I would align these numbers, like the voxel size. I would make the voxel size the same value as the Pyro source's particle separation. So usually you would just control copy parameter and paste it in here. So you just, once one parameter changes, the other one changes automatically as well. So they would always align at the same. Now this defines the quality of our Pyro. So this is what we get here. Let me see if I can change the quality. But every single time I change that parameter value, this would have to recook. So maybe I won't, because then it has to recook the entire simulation, because we don't start seeing it the shape until the later end of the simulation, like the higher frames. So maybe not. Let's try the Pyro Bake. So Pyro Bake here. This is the newer node in order to create a more pretty volume. Sometimes these volumes can get so nice that you can just render straight off of the flipbook, and that can just be a render. But let's go over some of the stuff here. Bake. So another thing to remember to tweak, not only the viewport, but also the max visualization resolution here. So I usually just add a 0 to max it out. It doesn't help much here because the volume is still low quality. So smoke here, it automatically is detecting the density attribute. So in our volume here, we have a density. Oh, I forgot to pin it, sorry. Okay. We have a density. A density, temperature, and V as in velocity volume. And we're going to get right into this V because this will become our velocity volume that we will feed into other simulations. But it does has a density. So the density is mapped, automatically is detected by this Pyro Bake volume, and it is mapped to color. And how is it mapped to color? Well, we have the density scale here. Let's make it 5 to make it thicker. So you can see that it becomes thicker. Let me scroll. Hopefully you can see that it's becoming darker. A little bit. Very subtle. You can control the smoke color. So I want a red color. So it instantly becomes red. Scatter. We'll give it more. I think it's such a low quality volume. It's not really seeing this. Temperature, I don't believe I have much. Yeah, it's not much of a temperature. Just because I think it's all being mapped to 1 at the moment. Let me see. Pyro source here. We can actually take a small peek at this. I just want the temperature. I want to see what the value is. They have input it by default. So its temperature is all 1. Not much variety. We can add a bit of fire, but the fire is, now it's so bright. The reason because the fire is so bright because it's taking it off the temperature. So if you're ever wondering how this node is getting all these values, click on the last tab over here, the bindings tab. And in the smoke, you'll see, okay, so the smoke is mapped, is directly getting the information from the density primitive. Okay, scatter is getting it from the temperature, masking the, like, it's doing something complex with the scatter. The fire is getting it from the temperature. And they have this secondary fire as well. And what the one I love about Pyro is the emission. So you can make things glow. I really like this, but we don't have a CE. So we can take this and map it to, let's map it to density just for fun. Just have some fun. You can see instantly it has something, it does something. So let me turn it off. Oh, it's not updating. Bake. Okay, let me do CE. Put the CE, it goes away. And then let's put the density back in. So it's, the emission is getting powering off of the density. So we're getting a red glow. Now let's take a look at what the emission color is. Let's see if we can, where's the emission? Oh, I don't think they have an emission. They should have one. I think it's just the red. It's controlled by this. Fire color ramp. I'm not sure where the emission color can be controlled. I'm still too used to this volume visualization one. So I'm more familiar with the old node. So let's take a look at this one, since this is the one I can show you more detail. This one, this Pyro Bake volume, I usually don't use this too much. Well, I don't configure it manually. I use this. What it can do, which is really, really handy, is create the material for you. So this makes it very easy. So based off of whatever you have configured here, and you can click this, it'll instantly create a volume material for you in the material network. So this is very handy. Density. I'm not sure where the emission volume, where you can control this. Or maybe you can't. Maybe you can't control the color. It's just something they hard coded that you can't control. You can only control it by tweaking the attribute values of the coming into the Pyro source. Actually, we can try that. So I'm going to take away the clean. Random attribute. Now, let me come over here and enable that again. So we can have fun with this. Sorry, that was just something that came into my mind. So it has a CE. So let's try that. Let's throw down an attribute randomize. And I'm just going to feed in the CE. Should be a scalar value. So I just need one dimension. Constant, not random. Let's give it a random number. Uniform discrete, sure. Value of 9, I think 1 should do. Now this is not changing. The change is not being propagated down just because this pyro source, I believe, is not taking it. Let me reset this. CE here. We need to add another one. Let's add a color velocity custom one. CE. Now let's see if this controls anything. Step size. Let me control this. Is the CE getting through? No, I'm not getting. Oh, the volume visualization. So once you add an attribute, so I'm trying to manually tweak this, controlling it using by adding an attribute, by adding the CE manually. So it's taking it into the Pyro source. But once it gets into the volume rasterized attribute, now it's taking by the volume source because I've added this section down here. So it's taking it. It's taking the CE. Now let's go to the volume visual rasterization. This turns it into a volume. If we look carefully here, we don't have a CE. There is no CE here. It's missing. So that means here we have to add it here. Add it in here. So it's converting the V, the density, and temperature into volumes. Now we got a new one, a CE. Let's see if that does it. Okay, so we finally get our CE there. That's what we wanted. Now let's take a look. Okay, finally we get something different. Now let's come back up here. We'll put the render flag on the Pyro bake volume, and then come up here to the random the attribute randomize. And I'm gonna move this around and see what we get, what it does to least. Okay, maybe a global scale. Maybe just do the global scale, because we do have a global scale here. Let's increase this to 1000. Well, that's not much fun. Oh, this doesn't update very well. Okay, let's lower this a bit. 10. So it does affect it. Makes it brighter. Oh, that looks nice. Sort of. No, you can use the volume as an emission color field for rendering or viewport visualization. Use the volume as an emission color field. Since the emission intensity is already baked into this volume, you should ensure that the emission intensity is constant 1. Oh. But I am creating a random attribute every single time. So I didn't want a constant one. But if it is being baked, I guess thus the name Pyro Bake Volume, it is baking it in. But our source is different every single time. So wouldn't that trigger the bake to update every single time? Okay. Well, okay. I spent too much time on the Pyro Bake Volume. Sorry about that. The volume visualization is something I'm more familiar with, and it's something I have prepared to make a little bit more prettier. Emission scale. So this volume visualization is a lot easier to control in my opinion, because it has an emission scale. It exposes this. We can map it right in. So I'm taking the V here and I'm mapping it directly to the emission. Let's see. Okay, to make it brighter. It's very thin because the smoke density is very thin. I'm going to lower this. make it a bit thicker. Okay. Because the density of this volume is very low, so I have to lower all my ranges. But this provides a direct access, so we can actually feed in the attribute right in here and then control the range to map it in. So I'm taking the V and mapping it into the emissions control. So the higher the velocity, the faster it turns, the faster it runs. It moves, the tornado moves. That will power this ramp, which is the emission intensity. And the bottom here will power the color. Make it a little lower so it's more red. So this is something I'm more used to rather than the Pyro bake volume. This we control the density, or you can control it on a global scale up here in the density scale. Okay, so I spent way too much time on these two things. All I really wanted to show you was the volume velocity. This is our volume velocity. Now we need to plug this into the Pyro and do a simulation. But first, I promised to plug it into the paper tornado simulation. So we're going to substitute. We're going to substitute what we had before here, which was powering off the pop force, which is this. It turns perfectly fine using the pop force. But now we're going to use the volume velocity that we've converted from a particle system. Now, in order to do that, we need to use a different pop node, which is the pop advec by volumes. Here, let me do this from scratch. Pop advec from by volumes. Gonna hook it up to the force. I'm gonna pick here. Here, I'm gonna pick what we had, which was the volume, what did I call that node? Let's go back. Which is this node here, which is what you see here, this guy. So I'm going to take this, Control C. So that will copy the path to that node. And I'm going to paste it in here. Enter. Okay. Let's just power it through. Now it doesn't do much right now. It does need a bit more power. Now, it does need a bit more power to push these vellum papers, because this vellum paper does have a density and a mass. So we do need to power it a bit more. This velocity scale here. And I'm going to put it to 10. And let's run it again. It's not doing anything, is it? The velocity volume I plugged in was very thin. This is something I wanted to show you. This is very thin. So it's not covering the entire simulation wherever the paper is. It's not covering the places where the paper is part of. This essentially is a vector field. It covers we're taking the particles, which is going in a certain direction. It has an instruction. Every particle has an instruction. Go left, go left, go left, or go right, go right, go right. And every single time, we convert that into a volume. So every voxel now has an instruction for every single frame. And when the particle lands or gets close enough inside that volume, our voxel, it receives an instruction and it goes like, okay, I can go right or left. But what if it never gets close to our tornado? So we're not covering the entire area, not covering enough of the area, enough to receive instructions, enough for the vellum paper to receive instructions. So how do we fix this? I simply just put down a pop replicate. So it's taking each point and making copies of each point, making more of each particle on a huge scale. So we get like a blob. But remember, in the pop replicate, you need to remember to check the copy source attributes. So you can copy the velocity as well. So we need all that good ingredient stuff. You need the, I believe the velocity and force become important. Let's see. So now our volume velocity looks like this. It looks much thicker compared to this. Come on. Okay. Much thicker. So we're covering way more area. Let me go back to that. So let's go back to that vellum and see if it works now, because I've made our volume velocity a lot more coverage. Well, okay, I think I made a mistake somewhere. The V. That's another thing I forgot to mention. What is wrong with me today? So the field name vel, it's taking the field name. This is the wrong field name that we've inputted here. Now you might be thinking, well, vel is velocity. There's nothing wrong about that. But let's take a look at what we have here. Let's actually go into this. So it brings us back to this. So it brings us back to this guy. Oh, it's okay. Into our blob. Let's take a look here. Pin this down, and we actually have velocity here, but it's V. It's not vel. So our velocity volume is named V. So let's go back. Yeah, let's go back here, and I'm just going to update this field name. I'm going to use V. Let's try this one more time. Oh, okay, sorry. V force. Okay, this should have worked. Oh. So you can okay, so this is not working out. Okay. And I know why. It's because I showed you how to convert it into a volume velocity that has. This is actually a vector volume. This is a vector volume. I meant to show you the other one first. Oh, today's so bad. I don't know what happened. I meant to show you this one first. In order to convert into a volume velocity, there are different types of volume in Houdini. They have the old school Houdini volumes, which are scalar volumes. And as I mentioned at the beginning, when you have your vectors, the vector has 3 components. It has the x, y, z. So you have your x, y, and z components. But how do you fit that into a scalar volume? A volume can only take the old Houdini volumes can only take one scalar value. It can only take one value. Either you get the x, the y, or the z, but not all 3. So in order to fix that, Houdini, in order to work around it, Houdini had made the velocity volumes into 3 components. Which is what you see here, the v.x, v.y, v.z. I meant to show you this first before I moved on to the other one. Move on to this volume velocity, which works for Pyro. Okay. So this is the old school, old volume, and it is converted. We do take the same particles, so I do have the same particles here. I don't know what this transform does. Oh, I'm making it bigger. So I am making this bigger to cover more area. And then I'm taking it and using that same trick, using the point replicate to making it thicker. So it's the exact same trick. The only difference here is that now we're using the volume velocity node in order to convert it into a volume, in order to convert all this stuff into a volume. The volume velocity node takes 3 inputs. We have a velocity volume. So it does need an empty volume to begin with. So that's what this is. This node here just initializes an empty volume. And it asks us, what kind of volume do you want? This volume here. And it asks us what kind of volume we want. So we're going to choose a vector volume, not a scalar volume, because a scalar volume only has one value. We want the vector volume. Since we have an XYZ component to fill, we have 3 components, so it's actually a vector. I'm going to make, what's the size of the volume? I'm going to make it 10, 10, 10. So it covers the whole particle area. It covers this whole area. Yes, okay. If you have trouble figuring out the size of the volume, what I usually do is template this so we can actually see the particles. Highlight, select the volume, move your mouse over here, press enter, and it'll give you a more manual way to tweak the box, to tweak the size of the volume. So you can see here that we don't need all this area down here, so I can move this up actually. So this would save a bit of CPU cycles because we're not using the one on the bottom. Okay, and I think this is okay. This is pretty good. So we want a little bit more space on the sides, just in case it expands any more larger. So we have an empty volume here. And then that goes into the first input of the volume velocity node. And then we take in, what is it asking for? Point velocities. It'll take in the point velocities, which is our pop net, and it'll actually create the volume velocity for us. It takes the 2 and it does its magic. In the volume velocity, in the points tab, right here, the points tab, add point velocity. And remember to choose points here. Just take all the attributes. Just take everything. It won't show up in the drop down though, for some strange reason. You can add noise to it too. So you can modify the volume velocity by adding curl noise or adding whatever noise or vortex. So it does allow you different features to modify the existing tornado motion that we have going on right here. I'm just going to leave it at that for now. Let's go with something simply. And let's copy this. And finally, hopefully get a working Vellum tornado look as promised. It was supposed to be simple. If I only showed you the right example. So now I have to update this link. So I'm pointing to this guy, the volume velocity vector that we have here, the v.x, v.y, and v.z. The old volume, scalar volume. And not this one. This was something I was supposed to show you a little later on in the video. I do apologize. And then we can pop it into the pop effect by volumes. Here, plug it in. The Houdini scalar volume that I labeled. Okay, now let's play it. It's cooking a little bit longer. I will zoom in just a bit. So now you can see something moving. It's finally doing something. Oops. Okay, I think that's good enough. It is a little powerful because I have jacked it up to the velocity scale to 10. I wonder if this would be a little bit better if it was just 1. I don't think 1 has enough power to push it. So you would need something like very heavy. Because, again, the vellum paper material has weight and it has mass. So you do need to pump this. You need to tweak it. It'll be by trial and error. You need to tweak this to find the right value, the sweet spot. Now, there are several ways to control it. If you want complete control, you could use update position. Now, this literally controls the position of all the particles and all the papers. And it follows the volume velocity almost to the T. Oh, I think we still need the volume scale to like something like 10. There you go. So it follows, using the update position, it follows the volume velocity more closely. But it's not getting all of them. It's not getting all of the vellum paper. And I think it might be because of my transform. I made it way too big. This is way too small. Let's take a look. Nope. The transform was okay. So it does take a bit of tweaking. You can see that I'm tweaking back and forth, trying to get that trying to get this to work. It is a lot harder to control using pop effect by volumes. So pop update position is not something I would use all the time, just because it doesn't give you a very natural look even when you get it to work. Update force and update velocity is the ones I usually stick with. If you want a more natural look. So this picks it up. There it goes. And it's still flying around. It's trying to match the volume velocity. Because it's expanding. The tornado twirls, and expands up there. So it's doing the expansion right now. It does look a little funny once it gets to the top. So, Boldoski, hello from Poland. I hope I got your name right. Okay, let me check my list. So, why not stick with just the pop force volume was what I wanted to get at. Why not just stick to that? It's so much easier to control. As you can see, I had so many, I plugged in the wrong volume and then it didn't even work. So that was something I went through unintentionally. That was a mistake I went through unintentionally. I simply just showed you the wrong volume. That was planned for later on in the video. But you can see that you come across all sorts of problems with controlling the volume. So why do we still bother with it? Why not just use this pop force? Or here, let me use the one that I showed you. That's the one we copied from Basic Concept 1. Why not just use this? This is simple, easy, and you plug and play. The reason behind this is because the volume, controlling it using a volume velocity is handy because it is reusable. You develop a volume velocity, you can use it for many types of simulations, not only Vellum. We can plug it into Pyro. We can plug in the same volume velocity into RBD. We can even plug it into Unreal Engine, into their Niagara system. I believe in Houdini there is a bunch of lab tools now to integrate. Yes, the Labs Niagara ROP. This will produce a volume velocity that you can plug right into the Unreal Engine, and you can have this power maybe the chaos system in Unreal Engine. You can make it do all sorts of things with the blueprints, which is useful for making games. So the applications are limitless. However, if you're just using the pop force, like the Vex code that we plugged in here, yeah, it's simple enough for this scene, but it's not very reusable. It's not as powerful. So you do have to do a bit more work with the pop volume velocity. This does require a bit more work, but the applications are way more flexible. Yes, it does. It can give you a more natural look as well, but it does take a bit of tweaking. Okay, and I think I skipped all the way down here. Feeding, yeah, that I already went through. Pop verse versus, yep, that I went through. Yeah, I skipped all the way down here. So let's go over the Pyro Sim. Let's plug this same tornado motion into the Pyro Sim now. And this is when I wanted to go over this volume velocity. So I was a little ahead of myself with this. This tornado. Oop. you see here. The point replicate to make it bigger, the P scale to control the size, volume, attribute, randomize. Oh, this was me just playing around with the emission. Let me just delete that. That was not planned. Pyro source and the volume rasterize attribute here. That turns it into a volume. So we got our volume here. What is note? The keynote to take away here is that this gets us a vector volume. So we have a single V here. This gets us a single V, as opposed to the other one. This way of doing it, using the volume velocity, gets us a vector volume with 3 components. It's a scalar volume, 3 scalar volumes combined together to give to produce the volume velocity and get all x, y, z components. In this one, it's more compact. There's like it's just one thing. It's one volume. Here we have 3 of them, which is the old sort of old Houdini volumes. Now, why don't we just use this new one? It's so compact, it's easy to use, it's something we're familiar with, and it's the workflow that you create a volume. This is the Pyro source, so everyone's familiar with using this workflow to create a volume, because this is what we use to create the mission for the Pyro source simulations. So why not use this? The thing is, it's not compatible with every single type of simulation. For example, in here, in the vellum, we can manipulate the vellum paper, vellum material by using all of these, where it's compatible with all the pop nodes. But I think the pop net hasn't been really updated too much in the later versions of Houdini. So it doesn't take this pop and vec by volumes does not take a vector velocity. Vector volume. It takes 3 scalar volumes, which is the old style we have here. So that's vellum though. For Pyro. Now let's move on to Pyro. So here I have a very simple, this will look super familiar now. Since I was explaining it, the wrong volume for like half an hour. I create a very simple Pyro simulation. It's a sphere. I did something fancy by matching the size, because I was using a torus at the beginning, and this was like the perfect size, but then I didn't like the hole in the middle. But I didn't want to adjust the size for the sphere. So I just used the match size to make the sphere the same size as the torus. Sorry, this is something I will take away later on, because this is just confusing. It's unnecessary for the match size. I was just getting lazy. And I feed that directly into a Pyro source. So I want to convert this into a volume, because this is going to be my Pyro source emission. We take this, we have the Pyro source here, and I'm using a particle separation of 0.035. We have density, we have temperature. Cool. There is this attribute adjust vector velocity. Trying to pull it, I believe it's trying to pull it in the middle. But let's ignore this. I believe I create this from the billowing, the Pyro configure. So now in Houdini 19, there's a bunch of already templates made for you for Pyro. If you type in Pyro configure, all these simulations are already pre-made. It's very much like typing in pop net, and it's already pre-made. Like everything here is pre-made for you, like a dummy template. That's what they've done with Pyro. If you type in Pyro configure, so everything you see there here is good to go. So I believe this was an artifact that I didn't delete. We then take the Pyro source, and then we convert this into a volume by adding a volume rasterized attribute here. So this is grabbing the density, the temperature, and the velocity. I don't think we have velocity here though. Yeah, there's a here. Let me show you this. So there's a density. There's a temperature from the Pyro source, but we don't have a velocity because this is the emission. We're going to actually add velocity to it. So let's take this and turn it into a volume rasterized attribute. But at least we need to rasterize the density and temperature, because that we have. So let's just check it. One way to check it is look into the details and see what kind of volumes are created. And we see that it's created the density and temperature volumes. Now, this is going to be our emission, our Pyro source emission. So let's go into a .NET. You can use this a different way. There is a new Pyro solver that you can stick right onto the SOP level, because Houdini sidefx has been trying to integrate all their solvers into the SOP level. I'm still old-fashioned, I guess. I haven't had a chance to play around with the Pyro solver right on the SOP level one. I'm so used to doing it in the .NET, so my example is in the .NET way. Now you can see here, I'm going to show you a constant feed of the volume source. So I'm going to ignore this one first. Now we have the smoke object every single time. Actually, I can do this. Let's do this from scratch. It's probably easier to explain. And maybe I'm less likely to make more mistakes. Okay, so we're doing a Pyro solver, Pyro simulation. The first thing we need, a Pyro solver. Let's drop that down. Now we need an output, because I deleted that by accident. I'll put the output flag here. Now we need a smoke object, just because I'm doing a smoke simulation. So let's add that. That always goes into the first input of the solver. Okay, we got something going on. Cool. Now let's hook up the initial data. So it's asking us, this smoke object, what is the initial emission? That's our Pyro source. That's that torus thing that we have over here, this out Pyro source. So I'm just going to copy this, go down, paste it into the density SOP path. So this is going to feed it in at the beginning for the first frame. And instantly you see your source, Pyro smoke right here. So let's just play it. It just disappears, just because the Pyro solver has come to the Pyro solver shape, and you'll see a dissipation. Shape, dissipation. So dissipation is set to 0.1. Well, we don't have much of a density at the beginning feeding in for the first frame. The volume is pretty low. So 0.1 makes sense. Now I want to constantly feed in something. And I just don't like this smoke object only feeds it in the first frame. which is very useful for like a burst, which is something I have over here as well, like a burst. So this one's cached. I'm going to play this one though. So this is just a burst. Whoa. Okay, there it goes. So it burst of Pyro. Okay, this is a little slower, but at least it's running. So this is one burst of smoke. It's only being sourced in once in the frame 1. So if you want an effect like the burst that I've shown you, you can add in your volume data in here. And then tweak the Pyro solver, and you can tweak the shapes and everything. Now we can actually tweak the density stop to make it 10 because we need a bit more density. And it just disappears because we don't have any forces acting on it. So the only force acting on it is the dissipation from the Pyro solver here, the shape. We can add, let's take that away and just go, I don't know, randomly add stuff here. So it's not doing anything yet. That's another thing you need to be aware of. You can see this white square or this cube that's sort of, you know that there's volume here. You see a volume inside this cube, but it's nicely packed right into the cube. Now, that's defining the bounds of the volume. So let's make the bounds a little bigger so the volume can actually expand somewhere. Select the Pyro solver, come over here, press enter. Sorry, come over here, press enter. Or was it the Pyro source? Oh, sorry. Select the smoke object. Come over here to the viewport and then press enter. And then you'll see that you can adjust the dimensions of the smoke. So we have more room to play around with. I think I need more room. Okay, now let's play it. Now you can see it slowly moves up a bit. That's because the buoyancy is probably set really low. So the buoyancy lifts it up, but at least you see it do something now because it's not being confined. Oh, that's another thing. I should make the bottom a little bit more because it's getting cut off on the bottom too. Okay, so slowly it's moving upwards, really, really slowly. We can increase that. The buoyancy. Here. Pyro solver here. Buoyancy here. So the buoyancy is set to, the buoyancy lift is 5. Direction is upwards. Fine. We can make it, I don't know, 50. Let's try it. It's still moving. It's a little faster. I wonder why it's so slow. Very, very slow. So I'm going to change this back to 5. That's not what I wanted to show you. Let me turn all these off first and turn the dissipation back on. Now I want to continuously source this piece with more smoke. Because if the only reason why the smoke lasted so long like this was because I turned off the dissipation. But that's not smoke. Smoke disperses and it eventually disappears into thin air. So smoke naturally has dissipation. Let's turn that back on and see what we have. The smoke just really quickly after 50 frames, it disappears. So we want to continuously source it and pump more smoke in. And in order to do that, we use a volume source node. Drop that down. And that goes to the last input over here. Now, before I want to do this, I want to add in a gas resize fluid dynamics. I know that's a mouthful. Gas resize. And it's the one on the bottom. This one is the one you want, not the one on the top, the one on the bottom. So this will update this bound. So you can see this white bound area here. Well, it's always calculating. Your computer is always calculating every single voxel within this white cube box. It's quite a lot because sometimes we don't need to. I mean, the smoke is like literally here, but our box is like this size over there. So that's a waste of all this space. All this space here, that's a waste of all this space. We don't really need. And that's what this gas resize dynamic will do. It will dynamically resize this cube smaller to a max. It will never exceed the limit that you set here, this large cube white box. It will never exceed that, but it can be smaller when necessary. For example, like this, there's no smoke here, then it'll get smaller. So that goes to the second input, which is the pre-solve. So we want to do all that calculations before we get into the Pyro simulations. So you can see the cube box instantly becomes smaller to the size of the smoke. So that will save us, it will speed up our simulation. Now back to this volume source. I want a constant feed into this volume source. So let's constantly feed it in. I'm going to come over, okay, let's go up here. And I'm going to choose this volume source. We're going to just use this for now. Copy that. Here. Volume source, plug it into here, the SOP. Okay. Sourcing smoke, initialize. So sometimes to get the fields automatically to populate, you have to like toggle this sync, but that's not what we want. We want to source the smoke and then flip it back. It'll automatically populate these vector attributes for us. The density to temperature, we do not have a velocity vector, as you remember from here, Pyro. We do not have a there is no velocity volume here. I have yet to put that in. Okay, so let's just try this. So this one won't matter. We can just take it out, actually. Okay, let's play it. Okay, burst. Finally, we get a burst until it hits the limit at the top that we set. So we finally get a burst. The point is that it's continuously feeding in more smoke from our torus. It's continuously feeding in. So we got unlimited amount of smoke. Okay, now we want to feed in our tornado velocity volume. In order to feed that in, but I only want to take the velocity. I don't want anything else. We use the same volume source. So I'm going to take another one. Volume source sources volumes in. So if we want to feed in a velocity field, we use the same source. But we have two of them. What do? We can merge it together. Okay, this one. So again, the same trick. Gonna flip it and flip it back. So this time I have all three. I know there's a density, I know there's a temperature, and I know there's a velocity. Let's go back up so we can get the path and plug it in here. Let's go back up and find our velocity volume. I've actually made it conveniently here. I already hooked it up. Let's take a look. So this is the scalar one that I have. And I just want to show you. This is the v.x, v.y, v.z. So let's be more illustrative, and I will go to the node network. I think that will jog your memory more. So that's this thing that I have here. The one that I was supposed to show you first for the Vellum simulation. But instead, I showed you this one first, which is actually supposed to be used for this Pyro instead. So that's the scalar volume. Now, the next one we have here is the vector volume. So let's take a look what this looks like. Pin. This is a vector volume. We can see that there's only one velocity vector. There's only one volume here. And it says vector 3s. So we know it's a vector volume. This here too. It says vector 3s. And to jog your memory one more time, that's this thing that I showed you at the beginning. Sort of like, I was supposed to show you to you now in the point of the video. Anyways, I gotta get over that. I'm sorry. Okay, now all three of these are hooked up. Now let's hook up the VDB, the vector volume. That's the one with just one, the newer volume with just one of them. Very compact. Let's hook it up to this. Now I'm going to take this and copy it, this path. Go to the .NET. Come in here. Come to the volume source. And let me get that handy thing. Sorry. Better box. Input SOP here. Okay, now let's plug it into the SOP right here. Okay, and then we're sourcing. I'm taking the density that's coming from this SOP and I'm mapping it to the density into this Pyro and I'm adding it. Well, I don't want to add that because I want the density to only come from the torus. So I'm going to put the 0 for this. The temperature. I'm actually not really interested in the temperature, but I'm going to have it add anyways. The velocity is the more important one. So we're taking, this is here to note, we're taking the V from the source volume. That's whatever our SOP was, and we're mapping it to the vel for the simulation because Houdini named the velocity vel in all of its simulations for some strange reason, which is not aligned with the SOP. It is like that, and it's been like that forever. So you just have to get used to it. So let's just go back just one more time. I just want to show you this here. It has the density. It has the density, it has the temperature, and it has our V. So those are the things that we're going to map in. That's what the volume source node is looking for. Now we can finally play it and see what happens. It's probably not going to be strong enough. I remember I had to pump it up really high. Okay, so we can only make out the volume source being pumped in constantly from the torus, but we don't see the tornado at all. Like, we don't see the tornado affecting it at all. Let's take a look. This is the size of our tornado. This is the size of our burst. So it's quite a big size difference. It's not strong enough to pump it in. What I'm going to do here is I'm going to turn off the buoyancy. So it doesn't go up at all. Oops. Smoke up. I believe it's the Pyro server. Simulation, buoyancy, lift. I'm going to turn this off. And what we should have is just a ball of smoke. Okay, definitely we're getting the ball of smoke. Now this guy is just too small and too slow. I think it takes up to like give it a second. Oh, is it cooking it? Oh, I didn't cache this. Okay, let's run something simple. This one is cached. It's still slow, but it's not as slow. Vector volume, come on. This one should be cast. I'm not sure why it's cooking. Unless I linked it incorrectly. It's linked to this one. This one is cached. Load from disk? Okay. Yep. So this was the one I was trying to get in. Okay. So these are the ones I cached out. To make this run more smoother, it was supposed to run more smoother. Let me just replace this one more time. Just in case. Okay, that looks good. So let's hook this one up. Because this one's cached. I'm going to just double check that we have the same... I wonder why it's like that. Okay. Stop. Yeah, we have the same vector volume here. We have the V here. And I've hooked it up to the out volume velocity. Now we're going to go into the .NET. Let's go back to frame 1. Let's go in here. Volume source. That is the same thing that is being hooked in here. The out volume velocity. Now let's try it. Let me see this. It's very risky to simulate such small stuff in Houdini. It is. It is. You do have to wait until the tornado builds up high enough to pull the smoke out. Okay, there you see it. The buildup was too much. Now I remember why I had that time shift over there. It was to skip the first 50 frames. You can start to see it pulling it up. I have to increase the velocity. Okay, let me pause it for a second so I can change the angle. Stop. Okay, you can see it start to pull up a bit. Very, very slow. Now I know why I had that. If you look closely, I had like a time shift here. It was to skip the first 40 frames. Let me skip the first 60 frames. And hook this all up. Because the tornado takes too long to build up. I hope I don't run out of cache frames though. Okay, back to here. So now we're skipping the beginning and come over to the volume source, and I'm going to increase the velocity because it's too slow. It's not strong enough. But I'm still adding though. So it's still adding. You can multiply it, but I find that adding it is more powerful. Okay, let's try that. Hopefully that'll speed things up. Well, I had a really snail look at it. At the same time, I'm going to open my notes. So it is peeping up there. Slowly, slowly, slowly. I wonder if it's because I'm streaming. This is taking so long. The Pyro solver has been Houdini. SideFx has updated Houdini to use the Pyro solver using the GPU to cook all the simulations for the Pyro. If you come to Pyro solver advanced and you see this, use OpenCL. This, if you check that box, oops. If you check this box up here, it will use your GPU and it'll cook a lot faster. The only issue is that I'm streaming. So that's already using the GPU to record and encode the video. I don't dare press this button. I do have 2 GPUs, but I don't know how to tell Houdini to use the second one and tell OBS to use the first one, which is the streaming software. The streaming software defaults to the first GPU that you plugged in. Apparently, every application on Windows defaults the first GPU you plug in. That's like the first PCIe slot that you plug into your hardware. Anyways, that's a little 2 cents. If you want a faster Pyro simulation to cook, remember to check this. Chances are your GPU will be a lot faster than your CPU. Not all the case though. It depends if you have what kind of hardware you have. But anyways, you can start to see it feed in. So this is only feeding in the velocity. We're finally getting the tornado into here. It's just taking forever. Apologize for that. Let's try something more interesting. Since I prepared a few of them. So let's go back over here. This is the one with my custom tornado. So I'm going to plug this straight in. So this is the weird twirling one that's going on. The one with the zigzag look. It looks incredibly funny when you convert it into a volume. Careful with OpenCL because it can eat VRAM pretty fast. It is true. It can eat it so fast with this mode on. Even on low res. That is true. You can't go over, like, your frame. You can't go over 240. Especially when I'm constantly pumping. Keep in mind, this node here is constantly pumping volumes in. It's constantly every single frame. This torus is getting thicker and thicker and thicker. More smoke is being pumped into this torus. So keep that in mind. The more smoke you have, you're gonna have use up more RAM. Okay, so we hooked up something else in here. So okay, we're getting better results here. This is the custom tornado that I modified, the zigzaggy look. That's this one you see. This guy over here. That's this guy. It moves a lot faster compared to the simple tornado that we had over here. This takes a while to build up. You can see here, like, it starts out really small. And this is already skipping the first 60 frames. It takes a while to build up to get to this. This one, the custom one I have so much modifications on it. It goes a lot faster. So let's just stick with this for now. So that's how you constantly source in the velocity. This is how I get my velocity field in. But what I wanted to show you is all these blobs that are coming up here and there. And let's compare it. I want a screenshot. Now, in order to view the Pyro in the SOP level, like, because we're one up now, we're no longer in the .NET level. You need a .dop import, just because I'm so used to the old .NET workflow. .dop import here, it extracts all that simulation stuff and brings it into the SOP context. So let's put it here. And let's take a look at what this looks like. This, now you can see the smoke was over here. Let me see if I can. I want both of them. Okay, that's just doing something on its own. What to do? Okay, I'll take a snapshot. Snapshot of this, and then I want to show you what is happening here. So this is a snapshot of it. The pyro, this pyro smoke simulation. Okay, this is not resizing. This is the actual size of the screen. A little higher side by side. So now the ground is sort of aligned. The smoke is all the way here. So we have smoke here. And here. And here. It has exceeded the area that does not have velocity volumes. So over here in this area, the velocity volume does not exist because our velocity volume is down here. It's this guy. This guy is our velocity volume. So anything up here, it's not getting any instructions. It's too far up there. It's not getting any instructions at all. And that results in these large blobs because smoke is being burst up, and it's just the only thing that's acting on it is dissipation because I turned off everything else. Let's take a look. Pyro solver. I turned off here. The only thing that's acting on it is dissipation. I turned off almost everything here. Combustion, we don't have much of a temperature, I believe. I even turned off the buoyancy lift. I mean, there are other things acting on it. There's like the cooling rate, there's combustion, but I have a constant temperature. So let's just focus on the shape of it because the velocity is driving the shape. Final render in Solaris, maybe? Probably not. I still haven't gotten the chance to learn Solaris yet. That's still on the list. I'm very used to using Blender, so it's like Houdini to Blender. That's been like my workflow forever. But I should get into Solaris. What else did I want to show you? Oh, the empty areas. So once it gets to these blobs, so you can see that once it gets to the blobby areas, you lose control over that. And in order to really work around that, I find that it's much easier if I do not source from an additional, because right now we're sourcing all the volumes from that torus. What if we don't source it from the torus? I just want smoke. What if I just wanted smoke to look like this, but more smoother, like not so spiky, because this is the volume velocity. I just want this volume velocity to drive the smoke. So I want that natural look of the pyro solver combined with this motion. So let's not, in the smoke object, we are, this smoke object, this is the initial body of smoke that was pumped in the first frame. Now I'm going to turn it off because I don't want it. The only thing I want to pump in is that velocity volume. So let's take this out. Let's take this out completely. Let's go to the volume source. Remember, this volume source is constantly pumping in stuff into that torus. And it's constantly pumping in the volume source, which is the torus, the smoke, which is this guy here. That torus thing that we have. Now I'm going to completely delete that. Let's remove it. I don't want it. We don't need this merge anymore either. So we just want, this is the velocity, volume velocity. not only will it pump in the velocity, I'm going to have it pump in the density as well. So now we can actually come back to the density. And I'm going to give it an actual value, like 1. And this is the only thing that's pumping it in. I removed everything else. So let's take a look. It has a bit more control, but it's going way too, like, you still see these blobs. Okay. Now I'm going to come to the Pyro solver and I'm going to turn up this dissipation. The blobs only exist because it's not disappearing. The smoke is not leaving. It's not dissipating. So let's turn this up. Something crazily 0.8. Not that much better. It's not. It is getting, like, it's disappearing. You can see it going away. Oh, it might just be touching the bounds. It's not going out fast enough. It's not disappearing fast enough. Let's try this. I'm trying to show you a way to work around to have the smoke follow closer to the volume velocity. We can always just pump in a 0.1. Yeah, this is a bit better. It's because my volume velocity is too fast and the other one is too slow. I didn't realize how slow it was during the cooking for when you're streaming. Let's turn this down. Let's turn down the volume, the velocity. So it moves a little slower. Okay, that's a bit better. It's not dissipating fast enough though. I'm adjusting this a little bit more. Disappear immediately. It's not disappearing fast enough. I wanted to show you an example where it disappears. It's best suited for the simple one. But the simple one's too slow. Let me increase simple tornado. Time shift. Let's increase this to 100. Okay, so it starts off like this. Oh, let's go 120 then. Let's skip it. I'm just trying to skip all the boring build-up. I do have it cached out, but I wanted to show you it live. I am sorry. I forgot to hook this up. So right now it's hooked up to my custom tornado. Let's hook it up to the simple one. Vector simple tornado here. Let's double check. Yep, that's the guy. Let's go in. Okay, we're starting to at least see the tornado shape. Pause it a second. Come here. It does take a while to build up. That's the only problem. Paper, fixed issue, poll. So that's the next thing I wanted to show you. This is adding velocity in. We're always adding velocity. There is another force that we can use. We're going to use the volume velocity and we're going to pull instead of add. So now we're starting to really see it. You can really see the tornado. Let's play it. This is really low voxel count. I apologize. It's just that I'm streaming. I don't dare put this, because this is a 0.2 division, which is very, very, very small. This is a very low resolution volume. This is 0.2 size. Generally, I would use 0.03, which is the one that you see. The volume velocity is 0.03. It's cached though. So it looks very, very pixelated at the moment. I do have renders though. I can show you. That is rendered out. That's something I can show you. There's our custom tornado. So this is the blobby one. The burst, because this is the example I want to show you where it exceeds the area of the velocity volume. Just gets out of control. Because the velocity, this is on the customized volume velocity. And that one goes really, really fast. I don't think I made one for the... I don't think I made one for the tornado one. Let's try and lower this a bit, because this looks really ugly. So I lowered it just a teeny bit. It's now running on 0.1. It looks a lot better though already. But it's a lot slower too. Okay, I want to stop it right here because I want to zoom in. It's still very pixelated, but hopefully you can get the point. How you source in, how do you use volume velocities with Pyro? You can keep adjusting it like here and there. There's also more things you can play around with. So now we have a tornado going up. But say we want the smoke to be pulling off of the torus. So I don't want it to be sourcing. This is sort of cheating. I'm sourcing it and forcing it to be the shape of the tornado shape. So I'm going to put 0 for this. I don't want to source it from that. And let's put back that torus shape. I want this to pull and sort of get a tornado out of it. Pull smoke out of this. So we're going to go to the smoke object, because this it defines the initial data for the first frame of the smoke, first body of smoke, which is not. Okay, let's put a 1 or 1, sure. Well, maybe 5. Here, and I'm actually going to change this velocity back to 1.3 because it needs something really, really powerful. I'm going to use a pole. So instead of add, I'm going to change this to a pole. And you can see that it has an acceleration strength. So I'm going to put this to the max. De-acceleration strength. And let's just try it. Oh, right. Sorry. Not only we have to... This is just the first body of smoke. We have to constantly source it. Because it dissipates right after. The first body of smoke only lasts for the first frame. So we want to constantly source that torus. And then use that tornado to pull it up. So the smoke becomes a tornado. Just going to take this, copy this, paste it in here, flip this again, flip it back. Okay, we have density, we have, was it 1 every frame? Okay, that should do it. Okay, it does take a while to build up. Okay, we're starting to see it peak. I think it's more interesting if we go up here, and then I'm gonna view this along. Can I template this or template that? It doesn't help. It does take a while to build up. To cook. It's taking awfully long. And it's not helping because I made it 0.1. I really wanted to show you how you can source a body of smoke and use the velocity volume to direct that body of smoke somewhere else, which is what I'm doing right here. So I'm pulling that body of smoke from the bottom and pulling it up in a tornado shape. It's just really, really slow. Okay, let's stop it. Even the playback is slow. Okay, so you can start, hopefully you can see the point. You can start to see the tornado being pulled up from this initial body of smoke that's constant being pumped from this volume source. That's what I want to show. So this is pulling. This is using pull instead of add. So this is another way to work around. It is a little tricky on controlling velocity volumes or vector fields, and when you're throwing it into a simulation, because you have so much going on. You have the velocity volume that's directing all the making directions, and you also have the initial solver forces that's acting on the simulation. So you have a lot that's going on, and it does take a bit of tweaking to get that right look. I have one last thing I want to talk about because, and I'm going to end it off because we're running on 2.5 hours, I think. Is that this at the beginning, my big bad mistake of talking about this volume velocity first instead of talking about this, the old volume velocity. So this one is the vector, the scalar volume one, the v.x, v.y, v.z volumes, the 3 volumes. Using this, it's only compatible with pop effect by volumes. But as you recall, we were just using this one to power the Pyro. So let's go back to the Pyro. So this is the Pyro. This is our Pyro solver here. This tornado is a vector volume. It's only one. And it says VDB 3. So it's a vector volume. It's a newer volume. It's not the Houdini volumes. The one, if we plug in the scalar volume here and we plug it in here, and this will not work with the pop effect by volumes. It won't understand this. It won't understand this 3-level velocity volume. Which was the same thing that happened when I plugged in the wrong volume type into the Vellum paper tornado. Nothing was happening. So I was just hitting myself in the foot for that one. So that's something you need to be aware of. There's 2 types of volumes, and you use it for some, it's compatible with some simulations, and sometimes it's compatible with other simulations. So that's something you need to be aware of. That's the last thing I wanted to talk about. And I do apologize one more time for messing up the volume velocity here and the 2 volume velocities. There is more to talk about, but I think we got almost everything. I think I covered almost everything, even the volume visualization. Well, not as much for this. Not as much as I wanted for this one. The Pyro bake volume, I'm not too familiar with, so that like I can talk about it, but it's not very well. So I'm just gonna end it off on this, and I want to thank everyone for watching it and surviving to the end of today's stream. It's a very, very long stream today, especially with that mistake I made in the middle. One more apology. If you have any questions, leave a question in the comments below, and I'll get to you as soon as possible. Happy Houdini!